On February 14th, 1990, at exactly 4:48 in the morning, a machine floating 3.7 billion miles from Earth opened its eye one final time, stared back at home, and then went permanently blind. Not because it failed, not because it crashed, but because someone deliberately chose to turn its vision off forever. What it saw in those last few seconds was so unimaginably small that it shattered something inside the human mind that has never fully healed. And today, in 2026, that same machine is dying in a way so quiet, so precise, and so inevitable that most of humanity doesn't even know it's happening. There is a moment in every great story where you realize that the ending was written long before anyone was ready for it. This is that moment for Voyager 1. And if you're watching this right now, you are witnessing something that only one generation of human beings will ever witness. The slow, irreversible final chapter of the most extraordinary journey any machine in human history has ever taken. Let's go back to where this story begins, because where it begins is everything. The year was 1977. The Cold War was still a daily psychological weight on the shoulders of an entire planet. The United States and the Soviet Union were locked in a competition so intense that space itself had become a battlefield of ambition. And inside that context, two spacecraft were assembled, loaded with instruments, strapped to rockets, and launched into the void within 16 days of each other. Voyager 2 left Earth first, on August 20th, 1977. Voyager 1 followed on September 5th, 1977. But despite leaving the launch pad second, Voyager 1 was placed on a faster trajectory, and it quickly overtook its twin. The plan was straightforward on paper, but staggering in scale. Fly past Jupiter and Saturn, study their rings, their moons, their magnetic fields, and then keep going. That was the mission. 5 years, maybe a little more. That was all anyone expected. What nobody expected was forever. Each spacecraft was equipped with 10 sets of scientific instruments designed for the planetary encounters ahead. There were cameras. There were infrared and ultraviolet. Spectrometers. There were magnetometers to measure magnetic fields, plasma detectors, cosmic ray detectors, and charged particle sensors. For the time, this was an extraordinary scientific payload, more sophisticated than anything humanity had ever sent beyond Earth's orbit. And when Voyager 1 reached Jupiter on March 5th, 1979, those instruments did not disappoint. What they sent back rewrote every textbook that had ever been written about the outer solar system. Jupiter was not the simple gas giant that astronomers had expected. It was a world of violent storms, a massive magnetosphere larger than the sun itself, and moons that were unlike anything ever imagined. Io, one of Jupiter's moons, was found to be actively volcanic. The first time volcanic activity had been confirmed on any world other than Earth. Europa showed signs of an icy surface that hinted at a liquid ocean beneath. These were not small discoveries. These were the kinds of revelations that fundamentally changed the direction of planetary science for decades. And then came Saturn on November 12th, 1980. 5 new moons. A new ring structures so complex and intricate that scientists spent years trying to understand them. Titan, Saturn's largest moon, was wrapped in a thick nitrogen atmosphere that made scientists wonder, seriously wonder, whether life of some kind might exist within it. Voyager 1 produced over 67,000 images between both spacecraft combined, images that transform distant smudges of light seen through Earth-based telescopes into real, breathing, complex worlds. Every single photograph was a gift. And then, in 1980, after the Saturn encounter, something important happened, something that set the stage for everything that came after. Because of the specific flight path required to get a close look at Titan, Voyager 1 was flung northward out of the plane of the solar system. It would not be directed toward Uranus or Neptune. Instead, it was now on a trajectory leading it toward the outer edge of the solar system and beyond. Its planetary mission was complete. And so the cameras, those extraordinary eyes that had shown humanity worlds it had never seen, were left running, watching the darkness, as the spacecraft climbed higher and higher above the solar system and moved deeper into the cold. But here is where it gets interesting. Because as Voyager 1 was climbing outward, there was a man back on Earth who had an idea. His name was Carl Sagan, astronomer, planetary scientist, and one of the most gifted communicators of scientific ideas that humanity has ever produced. Sagan had been part of the Voyager imaging team from the beginning. He had watched those extraordinary images of Jupiter and Saturn arrive on Earth. And now, as Voyager 1 continued sailing away into the void, he began lobbying for something that most engineers thought was pointless. Sagan wanted the spacecraft to turn its cameras around and take one last look at home, not because it would produce useful science. He acknowledged freely that it wouldn't. Earth would be far too small to reveal any meaningful detail. But Sagan believed it would produce something more important than science. He believed it would produce perspective. He lobbied for this for nearly a decade. There was resistance. There were concerns that pointing the camera so close to the sun could permanently damage the imaging system. There were engineering priorities. There were budget constraints. But Sagan kept pushing. And on February 13th, 1990, NASA finally sent the commands. It took hours for those commands to reach Voyager 1. And then, at 4:48 in the morning on February 14th, 1990, Valentine's Day, Voyager 1 turned its cameras toward home for the final time. It was positioned 3.7 billion miles from the sun, which is approximately 40 astronomical units, 40 times the distance between Earth and the sun. From that distance, it captured a mosaic of 60 images that together became known as the Solar System Family Portrait. 6 planets were visible in those images: Earth, Venus, Jupiter, Saturn, Uranus, and Neptune. Mercury was too close to the sun. Mars was obscured by scattered sunlight inside the camera. Pluto was too small, too dark, too distant to be detected. And Earth. Earth appeared as less than a single pixel of light, a fraction of a dot suspended in a band of sunlight scattered by the camera. That image became the most philosophically significant photograph in human history. Carl Sagan called it the pale blue dot, and the words he later wrote about it are so powerful that they bear pausing on even now. He spoke of how every king and emperor, every saint and sinner in the history of our species lived their entire lives on that barely visible mote of dust. Every war ever fought was fought over a fraction of that dot. Every mountain climbed, every ocean crossed, every civilization built and destroyed, all of it contained within something too small to measure from the edge of our own solar system. 34 minutes after that photograph was taken, at 4:48 a.m., Voyager 1 powered off its cameras. Forever. The software that controlled those cameras was subsequently deleted from the spacecraft's computer system. The computers on the ground that could analyze and process the images no longer exist. The cameras themselves, after years of exposure to the brutal cold of deep space, are almost certainly no longer functional. Even if NASA wanted to turn them back on, which it doesn't because it can't, there's no mechanism remaining to do so. The eyes of Voyager 1 closed on February 14th, 1990, and they will never open again. What you see in those final images is all you will ever get. The most distant photograph of Earth ever taken, and it shows our entire world as something smaller than a grain of sand. Think about what that means. Really think about it. Now here is where the story shifts from poetic to something altogether more profound, because Voyager 1 did not stop. The cameras went dark, but the spacecraft kept moving. It passed beyond the orbit of Neptune. It climbed into the outer reaches of the solar system, into a region called the heliosphere, the enormous bubble of charged particles. Magnetic fields generated by the sun that extends out well past the orbit of Pluto. For decades, astronomers had theorized about what lay beyond the boundary of the heliosphere, a region called the heliopause. Nobody had ever reached it. Nobody had ever been able to directly measure it. And then on August 25th, 2012, Voyager 1 crossed that boundary. The instruments on board detected the sudden change in the character of the surrounding particles. The solar wind dropped away, and the density of interstellar plasma increased. Voyager 1 had become the first human-made object to enter interstellar space, not just the first to leave the solar system in a symbolic sense, but the first to physically, measurably cross into the medium that exists between the stars, the space between suns, the cosmic ocean itself. And it is still there, right now. As you watch this, Voyager 1 is sailing through interstellar space at approximately 35,000 miles per hour, around 3.5 astronomical units per year. It is currently about 25.4 billion kilometers from Earth. To put that in a different frame, a signal traveling at the speed of light takes nearly 23.5 hours to cross that distance. Nearly a full day just for light, the fastest thing in the universe to travel between Earth and this spacecraft. And by November 18th, 2026, just months from now, Voyager 1 will have traveled so far that communications will take exactly 24 hours to reach it. One light day from Earth. No human-made object has ever been that far from our planet. On November 18th, 2026, at 2:16:07 in the morning, Pacific Standard Time, Voyager 1 will cross that threshold. It will be 16,094,799 times, 96 miles from Earth. Another historic first, for a mission that has been setting historic firsts since before most people alive today were born. But here is what is happening right now in 2026 that most coverage is not fully explaining. Voyager 1 is not just setting records, it is dying. Slowly, precisely, and in a way that its engineers have been preparing for with clinical precision for years. And understanding how it is dying tells you something important, not just about this spacecraft, but about the nature of exploration itself. Voyager 1 is powered by 3 radioisotope thermoelectric generators, RTGs. These are devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. When the spacecraft launched in 1977, those RTGs were generating approximately 470 watts of power. Not a lot by modern standards, less than 5 standard light bulbs, but enough to run the spacecraft and all its instruments for the planetary flybys. The problem is that radioactive decay is relentless and indifferent. The plutonium does not care about the mission. It does not slow down because scientists still want the data. It keeps decaying at its own fixed rate, and every year, both Voyager spacecraft lose approximately 4 watts of power. 4 watts. Almost nothing. On Earth, 4 watts is the difference between a slightly brighter phone charger and a slightly dimmer one. On Voyager 1, 4 watts is the difference between life and death. As of April 2026, the RTGs on Voyager 1 are producing less than half the power they generated at launch. The power margins are not just thin, they are razor sharp. Every decision the engineering team makes about the spacecraft is now filtered through a single terrifying question. How many watts does this cost? Heaters that keep fuel lines from freezing, transmitters that send data back to Earth, scientific instruments that measure the interstellar medium, all of them are in competition for the same shrinking pool of electricity. And that competition has consequences. The consequence is this. Over the decades since the planetary encounters ended, NASA's Voyager team has been turning off instruments one by one. Not because the instruments failed, not because the science wasn't valuable, but because there was no other choice. Of the 10 original instrument sets that each Voyager carried, 7 had already been shut down before this year. Cameras went in 1990. The ultraviolet spectrometer went silent. The plasma science experiment was turned off. The photopolarimeter system went dark. One by one, each instrument became a sacrifice made to buy the remaining ones more time. And this process accelerated. On February 25th, 2025, NASA shut down Voyager 1's cosmic ray subsystem, the instrument that had been measuring high-energy cosmic rays streaming in from deep space. It had been running for nearly 48 years. And then something happened on February 27th, 2026, that forced the engineering team's hand again. During a routine roll maneuver, a planned movement to maintain the spacecraft's orientation, Voyager 1 experienced an unexpected drop in power. The drop was dangerous. It nearly triggered the spacecraft's undervoltage fault protection system, a built-in failsafe designed to automatically shut down components to keep the probe in safe mode. If that system had triggered, the recovery process would have been long, difficult, and carried its own serious risks. The engineering team recognized they were operating with essentially no margin for error, and so they made the decision that had been coming for months. On April 17, 2026, NASA sent a command from Earth to Voyager 1. That command took approximately 23 hours to arrive. When it did, after a shutdown sequence lasting 3 hours and 15 minutes, Voyager 1's low-energy charged particles experiment, known as the LECP, went silent for the first time in almost 49 years of continuous operation. The LECP had been the instrument that measured low-energy ions, electrons, and cosmic rays in the interstellar medium. It had detected pressure fronts and regions of varying particle density in the space beyond. The heliosphere, data that no other spacecraft in existence can provide, because no other spacecraft in existence is where Voyager 1 is. That capability is now gone. The same instrument had been shut down on Voyager 2 in March 2025. Now both spacecraft have lost this eye. And what remains on Voyager 1, as of today in July 2026, is exactly 2 science instruments. 2 out of the original 10. The first is the plasma wave subsystem, which listens for plasma oscillations and radio frequency signatures in the surrounding interstellar medium. The second is the magnetometer, which measures the local magnetic field. These 2 instruments represent the last sensory capability of humanity's most distant explorer, and they are, by all accounts, still working, still sending back data, still describing, in the language of charged particles and magnetic fields, a region of the cosmos that no probe before Voyager 1 has ever directly sampled. The data they produce is irreplaceable. No telescope on Earth or in orbit can replicate what those 2 instruments do, because they are there, physically present in interstellar space, measuring it directly. And this is not a small thing. A 2021 scientific paper by researcher Stella Acker and colleagues demonstrated that the plasma wave data from Voyager 1 could be used to trace the density of interstellar plasma across a vast region, revealing persistent plasma waves in a medium that was previously assumed to be far quieter than it actually is. The science is still happening. The mission is still alive, but the clock is running. And here is where the story takes one final stunning turn, because NASA's engineers are not going quietly. They never have. This is the same team that, in 2023, discovered that Voyager 1 was sending back corrupted data due to a fault in one of its flight data computers, and managed to diagnose and fix the problem from a distance of 15 billion miles using software patches transmitted across the void, waiting nearly 2 days for confirmation that each fix had worked. This is the same team that revived long-dormant thrusters in 2017 that had not been fired since 1980, successfully extending the mission by 2 to 3 more years. These engineers do not accept defeat. They find another way. The plan they have devised is called simply the Big Bang. And the name is not accidental, because what they are proposing is nothing less than a complete simultaneous restructuring of how power is managed across the entire spacecraft. The Big Bang involves turning off a group of powered devices all at once, specifically 3 devices that have been used to keep the thruster fuel lines from freezing, and simultaneously switching on 3 alternative devices that perform the same thermal function but consume almost 10 watts less power combined. 10 watts. On Voyager 1, in 2026, 10 watts is enormous. 10 watts could be the difference between losing the next science instrument in months versus keeping both instruments alive for another year or more. It could potentially generate enough surplus power to restart the LECP, which engineers deliberately left in a state where a tiny scanning motor continues to run on just half a watt, precisely to keep that option open. The plan is being tested on Voyager 2 first, since Voyager 2 is slightly closer to Earth and has marginally more power available, making it the safer test subject. Testing on Voyager 2 is scheduled for May and June of 2026. If those tests succeed, the Big Bang will be attempted on Voyager 1 no sooner than July 2026. The outcome is uncertain. Attempting changes this significant on hardware that is nearly 50 years old, operating at temperatures that would destroy most electronics, at a distance where a single command takes nearly a day to arrive and another day for the response to return. This is not engineering under normal conditions. This is engineering at the absolute edge of what is possible. If it works, Voyager 1 could keep its remaining science instruments alive potentially into the late 2020s or even the early 2030s. If something goes wrong, the mission could end far sooner. The radioisotope thermoelectric generators, according to NASA's projections, may supply enough power for basic engineering communication until approximately 2036. But keeping a science instrument alive requires more power than just maintaining the transmitter. The final science instrument, whichever one goes last, is expected to fall silent sometime in the early 2030s if the Big Bang succeeds and no unforeseen failures occur. After that, Voyager 1 will still technically exist. It will still be out there, sailing through interstellar space, but it will be silent, not transmitting science, not measuring anything, just moving endlessly at 35,000 miles per hour through the dark, carrying its golden record on its side. And this is perhaps the most profound dimension of this entire story, the one that puts everything else in context. Before Voyager 1 left Earth, NASA attached to its body a message, not a scientific message, not an engineering schematic, a human message. The golden record, a 12-inch gold-plated copper disc, contains 115 images from Earth, spoken greetings in 55 languages, sounds of nature from thunder to whale song, music from dozens of human cultures including Bach and Beethoven and Chuck Berry, and traditional compositions from cultures across every inhabited continent. It contains recordings of a human heartbeat, of laughter, of a mother comforting a child, and inscribed within it, in a form that any sufficiently advanced civilization might conceivably decode, are the coordinates of our solar system, a map home. Carl Sagan described the golden record as a message in a bottle thrown into the cosmic ocean, and that is exactly what it is. The copper of that record, protected by a gold-plated aluminum jacket, is estimated by some scientists to remain physically intact for hundreds of millions of years in the near vacuum of interstellar space, long after Earth has changed beyond recognition. Long after. Every human being alive today is gone. Long after the civilizations that built this spacecraft have risen, transformed, or collapsed. Voyager 1 will still be out there, carrying that record, moving through the space between stars. It will not reach the vicinity of any other star system for approximately 40,000 years. And even then, it will not pass close enough to any star for that to be considered an encounter. It will simply keep going, into a darkness so vast and so deep that human imagination cannot fully contain it. What we are watching right now, the instrument shutdowns, the power calculations, the Big Bang gamble, the light day milestone approaching in November 2026, is not simply the end of a space mission. It is something more existential than that. It is humanity watching its own reach contract. Voyager 1 has been our outstretched hand into the unknown for nearly half a century. It has given us Jupiter's volcanic moons and Saturn's sculpted rings. It has given us the first portrait of our own solar system seen from outside, and a photograph that reduced our entire world to something smaller than a pixel. It has crossed into interstellar space, physically entered the territory between the stars, and reported back what it found there. It has done all of this on technology that has millions of times less computing power than the phone in your pocket. It has done all of this on a power supply that is now generating less electricity than a handful of ordinary light bulbs. And when the last signal falls silent, when the final science instrument powers down somewhere in the 2030s, and the data from the edge of everything stops coming, what will we be left with? We will be left with decades of data still being analyzed by scientists who are, in some cases, building entire careers on what Voyager 1 has already sent back. We will be left with the pale blue dot, that impossible photograph, that fraction of a pixel that contains everything we have ever been. We will be left with the knowledge that one of the first things we ever did, when we first truly reached for the stars, was to build a machine worthy of the journey. And we will be left with a question that hangs in the silence where the signal used to be. Out there, beyond everything we can see or measure in interstellar space, in the dark between suns, that golden record is still moving. The brainwaves of Anne Druyan, thinking about falling in love with Carl Sagan, are encoded on that disk. The laughter of a human child is on that disk. The music of Earth, all of it, is on that disk. If something ever finds it, what will they think of us? And more importantly, will we still be here to find out?